Now consider the industrial noise or the man-made noise, and the name, as the name suggests, that industrial noise or man-made noise is not a natural. It is made by this noise. Source of this noise is actually made by human beings, and these source may be uh, the noise generated by automobile, the aircraft ignition, then electrical motors switching gears, then leakage from high voltage lines and other heavy electrical machines. These are the major source of this type of noise, and this type of noise is very severe near the industrial region. Also, fluorescent lights are also another powerful source of this noise, and obviously because of this reason, these fluorescent lamp lights should not be used where sensitive receivers are installed. Uh, the noise is usually produced by the arc discharge present in those uh, automobiles, then all those sources that I have said earlier. Uh, and obviously, since these noise are generated by these heavy electrical machines, so this noise is severe and intense in industrial and densely populated areas. The nature of this noise is so variable that it is difficult to analyze and model this noise on any basis other than statistical. So we have no other choice but to use statistical analysis. Now we will discuss the internal noise. The source of the internal noise is present within the uh, system generally. So it is not coming from the external source, external body. It is coming due to the components used to make or implement the communication system. Most of the time this noise is actually arising because of the fluctuation of electrons through the devices that is used to make the communication circuits. And such electronic or electrical uh, devices, components may be anything, like even a small length of a conductor may be a potential source of noise, like resistor, capacitor, everything whatever we are using, a triode or a transistor, FET, whatever may be the type of component, all the components will generate some kind of noise, and that noise is the internal noise. Now we can divide, in a broad sense, we divide this internal noise into two categories. One is the short noise, another is the thermal noise. But there are several type of uh, noise present in the uh, in in different components. So let us try to understand these components one by one. So first consider the short noise. This noise arises in electronic devices maybe because of discrete nature of current flow in the device, and in solid state devices it arises from the random diffusion of minority carriers and the random generation and recombination of electron hole pair. When this noise is amplified and fed to loudspeaker, it sounds like a shower of lead shots striking a metal plate, and that is why it is called the short noise. The power spectral density of this type of noise may be drawn in this way. This is the PSD of short noise, and as you can see that near lower frequency range the short noise is almost flat, then it used to decrease, and it is almost flat up to a frequency of 80 megahertz, and then it decreases. Next comes the partition noise. Partition noise occurs when current has to divide between two or more paths, like this. So current has to divide in two or more paths, then we have this type of noise. And the result from the random fluctuation in the division. Here we have some random fluctuation of the electrons. It is thus expected that the diode would be less noisy than a transistor, and it is for this reason that the input of microwave receiver are often directly taken to the diode mixers. The spectrum of partition noise is almost flat. Active three-terminal components in which the control of terminal draws less current are less noisy, quite obvious. There is another kind of noise called the flicker noise. Flicker noise. Below few kilohertz frequencies, below few kilohertz frequencies, a component of noise appears, and the power spectral density of which increases as frequency decreases. That means the power spectral density of this noise may be like this. This is the PST. So lower the frequency, higher will be the noise power. So this type of noise is called the flicker noise. In semiconductor devices, flicker noise results from fluctuation in carrier density and is more troublesome in semiconductor amplifying devices at low frequencies. The fluctuation in the carrier density causes fluctuation in the conductivity of the material. This in turn produces a fluctuating voltage drop when a direct current flows, which is the flicker noise voltage. It follows that the mean square value of flicker noise voltage is proportional to the square of the direct current flowing. But we are not going for any mathematical analysis of this kind of noise. There is another noise called transit time noise. Transit time noise. In semiconductor devices, when a transit time of carrier crossing a junction is comparable with the time period of the signal, some of the carriers may diffuse back to the source or emitter. And it can be shown that this gives rise to an input admittance in which the conductance component increases with frequency. This conductance has a noise current source associated with it in parallel. Since the conductance increases with frequency, the power spectral density also increases. This is another kind of noise is present. So there is another noise called the generation recombination. Generation recombination noise. In semiconductor devices, some impurity centers will be ionized on a random basis, being energized thermally. Thus, the random generation of carriers occur in semiconductor devices. The carriers can also recombine with ionized impurity centers on a random basis, either directly or through trapping centers. The overall result is that the conductivity of the semiconductors have randomly fluctuating component, which gives rise to a noise current when directly current flows through the semiconductor device. The power spectral density of this type of noise is not well understood, but still there are certain kind of this type of noise is there. Next, we will try to understand the thermal noise. This arises due to the random motion of free electrons in the conducting medium, such as resistors, and actually anything. Each free electron inside a resistor is in motion due to its thermal energy. The path of individual electron motion is random and is zigzag. So if you consider this as a block, electrons never go in a straight fashion, rather it will follow this type of zigzag path because of different type of collisions. And the collision may be with the lattice structure. The net effect of this random motion is that there is no preferred direction of the flow of group of electrons, and as a result the average current is zero. On the contrary, because of the random motion of the individual electrons, there is a finite value of the RMS current. So there is no average current. Average current may be zero, but there may be some RMS current. So power spectral density of this current can be due to these free electrons may be written in this way: 1 plus 2 pi into f by alpha whole square. So maybe like this. Here K is the Boltzmann constant, T is the absolute temperature, and G is the conductance of the resistor. Alpha is the average of the collisions per second of an electron, and alpha may be of the order of say 10 to the power 14 or something like this. So obviously this part is negligibly small because the frequencies that we are using, generally we are using RF range. So f by alpha is of the order of 10 to the power 14, it is negligibly small. So essentially this SIF, so if this portion is negligibly small compared to 1, then essentially this SIF becomes almost constant. That means SIF can be written as 2kT into G, because this one is negligibly small. So it is almost straight. If you plot it, it will be almost straight. So the power spectral density of noise is considered to be constant, and the distribution of any circuit is determined by the bandwidth of the circuit. Thermal noise may be considered to contain all frequency components in equal amount. For this reason, thermal noise is often referred to as white noise because of this reason. White means equal amount of color present in the light. That light is called the white light. So with this analogy, we will call it as white noise. This is also called the Johnson noise. This thermal noise is also called the Johnson noise. Now consider just a resistor with R equal to 1 by G. So if we want to model this resistor, the noisy model of this resistor, we can draw in two ways. One is the Thevenin equivalent model, another is the Norton equivalent model. So let us see how we can model this. This is the Norton equivalent model, and also we have Thevenin equivalent model. And obviously these two models are related. VNT equal to R into INT. Now the power spectral density is the function of the square of the signal. The power spectral density SVF of the noise can be expressed in terms of power spectral density SIF of the noise current. So SVF can be written as R square into SIF. So that we can write it as 2kT into R, because R equal to 1 by G. SIF is this, R equal to 1 by G, so 2kTR. This is the power spectral density of the voltage, noise voltage. Now from the interpretation of power spectral density, the power carried by the frequency component of delta F Hertz centered at frequency say F, can be written as delta P equal to 2 SV delta F equal to 4 k T R into delta F. So if the noise voltage Vn is filtered by a narrowband filter of bandwidth delta F Hertz, the output voltage delta Vn of this filter will have a mean square value of delta Vn square bar equal to 4 k T R into delta F. Now we will consider another hypothetical noise, rather it is the white noise. The white noise is actually useful for the analysis purpose, and this white noise is termed in this way, is said white because it is assumed that all the frequency components are present in that particular noise equally, and the uh, the power spectral density of this white noise process is represented by, say, in this way, in 0 by 2. The factor, this factor half, has been included to indicate that half of the power is associated with the positive frequency and other for the negative frequency. The quantity n0, this one, has a dimension of watt per hertz and is of the order of, n0 is of the order of k into T. K is the Boltzmann constant and T is the absolute temperature. So power spectral density of this noise can be plotted in this way. All the frequency components are equally present. This value is in 0 by 2. This one is F. The autocorrelation function of this noise process is n0 by 2 into delta tau. So that is equal to this one. n0 by 2 into delta tau. That means this autocorrelation function is 0 when tau is not equal to 0. So it exists only at a particular time, and it doesn't exist in all other times. Now we will try to understand the noise figure of an amplifier. Noise figure of an amplifier. Well, noise figure may be defined in various ways. Actually, we have a term called signal to noise ratio. Signal to noise ratio, that is defined as the signal power to the noise power. But that particular parameter may not be suitable to determine the performance of the receiver. So we need some other parameters. So we can define the noise figure F bar of an amplifier as the ratio of the total noise power in the load, ratio of total noise power in the load to the noise power delivered to the load by the source alone. So this is called the spectral noise figure. We can define because now in terms of power spectral density or power density spectrum, it is the ratio of the total noise power density in the load to the noise power density delivered solely due to the source. That is called the spectral noise figure. Spectral noise figure, that can be written as SNTO by SNSO. Where this SNTO is the power spectral density of the total noise at the output of the amplifier, and SNSO denominator is the power spectral density of the noise at the output due to the source only. And that can be written in the alternate form as 1 plus SNAO by SNSO, where this SNAO is the power spectral density of the noise in the load solely due to the amplifier, because we are determining the noise figure of an amplifier. And so this is one of the definition of this noise figure. The average noise figure can be written as average of noise figure is 1 plus NAO divided by NSO. This NAO is the noise power at the output due solely to the amplifier, and NSO, the denominator, is the noise power at the output due solely to the source noise. So this is how we can define this noise figure. Generally, noise figure is written or expressed in terms of decibel. So decibel, we have to write it in this way. So minimum value of f bar, minimum value of f bar is equal to 1. So in decibel scale, that means if the amplifier is completely noiseless, then it will be taken as 0 dB. So this is the minimum value of the noise figure. For cascade system, that means if we have a number of amplifiers connected in cascade, then the overall noise figure can be written as f1 plus f2 minus 1 by g1 plus f3 minus 1 by g1 g2, etc. That means the system is like this. This one is say noise figure is f1, gain is g1, noise figure is f2, gain is g2, and so on. So if we have this type of system, then the overall noise figure of this system will be like this. So more the number of stages, we have to add them up. But thing is that from the second term, this f2 minus 1 is divided by g1. So if you can make this g1 very high, then this contribution, since g1 is divided throughout all the rest of the terms, with all the rest of the terms. So obviously if g1 is made very high, then these contributions to all these terms will be negligibly small. And if you can make f1 small enough, then obviously this value of f, the equivalent value of f, would expect it to be low. That is why for a cascade system or a long chain of receiver, means when the receiver consists of number of blocks, then the first stage of this block plays an important role, because first stage must have very low noise and high gain. Because of this reason, if we can make less noisy, so f1 will be lower, and if you can increase the gain g1, then these contributions will be very very small. So overall f, the noise figure, would expected to be smaller. Lesser the noise figure, better will be the system.